Sorry guys, I'm here. Stick with me. Just trying to line this up right. I guess it looks all right. Sorry guys. Okay, so you guys, today we are going to show, oh, you know what? We're gonna do this first. We're going to introduce what's called Vsepr theory, and it's going to allow us to determine the actual shapes of molecules. For example, right, I'm taking in oxygen. Here's some oxygen, right? I take that in, and then what do I breathe out with my hot funky breath? Carbon dioxide. So this would be kind of models for how we would expect these molecules to look. So what we're going to use is a theory called Vsepr theory. Okay, and so that's an acronym. So you guys, let's try to figure out what this acronym is. V, what do you guys think V? Think about a word that you guys are familiar with. You got it, valence. V for valence. S, what do you think? We've talked about a lot about an S word, shell. Valence shell. E, that's an easy one, guys. Come on, E, electron. So what are we interested in, guys? We're interested in the valence electrons in the outer shell, or the electrons in the valence outer shell. P, electrons exist as pair. You guys remember when we did Lewis structures, we were talking about shared pairs of electrons and lone pairs of electrons. And then R, what do electrons, how do they interact with each other? They repel. So what Vsepr is valence shell electron pair repulsion theory. Okay, so we're going to put that together and we're going to see what do these look like. Let me see if I'm lined up right. Not quite. We good? Almost there. Okay, so you guys, we're going to look at things. So you guys should write this, have your piece of paper, put it like sideways so you can put this across the top, long ways, and then here. So we're going to look at the Lewis structures of these. From that, we're going to determine the shape. You guys probably aren't even seeing me, are you? Yeah. So we'll go over here so you can at least see my big old fat head. We're going to determine the shape. We're going to determine the bond angles, the polarity, and then we're going to do what's called a Fisher projection. Okay, so we're going to go kind of quick here, okay? So, first thing is we've got to do a Lewis structure. We're going to put the atom that we, first thing is we're going to determine the number of valence electrons. So you guys would have to look at the periodic table. So I'm looking at the periodic table. Here, let me show you guys how you can do that. So first thing I'm going to do is I look at silicon, Si. Silicon is right here. If I count across in that period, it's 4. So silicon has 4 valence electrons. And then if I count across for oxygen, if I count across here, oxygen's 6. So oxygen has 6, but there's 2 oxygen atoms, each with 6, which is 12, plus the 4 from silicon is 16. Okay. Then I'm going to put the now I'm going to arrange the atoms. I'm going to put the one, remember the hint is, this is from your previous notes, I'm going to put the one that I expect to form the most bonds in the middle. Well, look at where silicon is. Silicon's right here. And you guys see it would need 4 extra electrons in order to fill its outer shell, whereas oxygen's right here only needs 2. Therefore, I would expect silicon to form more bonds than oxygen, and therefore I'm going to put silicon in the middle. So I put silicon in the middle. And you guys would probably guess, where would you put oxygen? I'd probably just put them on the sides. You know, and that could change, but at this point, that's what I do. You guys remember, right? If they make up a compound, they have to be bonded together. So I'm going to show a bonded pair of electrons. Each represents a shared pair of electrons. Remember? So this is 2 and this is 2 there. That's 4. Total 4. There was a total of 16. That means there's still 12 more. Now I'm going to just put them as lone pairs. 2, 4, 6, 8, 10, 12. Now maybe some of you guys might have put them over silicon. That's all right. You know, because you remember, do it in pencil because we might end up erasing. So remember, the last thing is we want to see if the octet rule is satisfied. So I look at every atom. Here, oxygen, 2, 4, 6, 8. Oxygen's good. Look at this oxygen. 2, 4, 6, 8. That's good. Now what about silicon? Is silicon happy, fat, content, stable? 2, 4. No, it only has 4 valence electrons. So that tells us that this is not the correct Lewis structure. So that what you do is you take a lone pair and then you make it a shared pair. So I'll take one of these lone pairs and maybe make it a shared pair. And then maybe you're thinking, okay, this one's still not, and I look at silicon, is it satisfied yet? 2, 4, 6, so it's almost there. But then, oh, it's not. So what I can do is take another lone pair, make it a shared pair. And you guys might choose different ones and then you might have to erase it and try it again. But now I look, This oxygen's good, 2, 4, 6, 8. Remember, each of those lines represents a pair of shared electrons. Look at silicon now, 2, 4, 6, 8. That's good. And then oxygen, 2, 4, 6, 8. That is the correct Lewis structure. So now we want to do the three-dimensional shape. What would this molecule actually look like? Well, here's how you do it. You look at the center atom, and you look at how many regions of electrons around the center atom. Now, you guys, even though these are two shared pairs of electrons, they kind of make up the same area of electrons. You kind of call it an electron domain. So this would like represent one electron domain, this is another. So basically, I have two areas of electrons around a central atom. So now the question is, how do you guys think, and you guys remember, what do electrons do? They want to repel each other. They want to be as far apart from each other as possible. So think about it. So if you have this, so we've got, let's say, a silicon atom, and we've got two oxygen atoms. The question is, how do you think the oxygen atoms would arrange themselves around a center atom so that they would maximize the distance between it? You guys, would you expect it to be like this? No. Is that the best they can do? No, I think you guys already know. How's the best that they can arrange themselves to maximize their separation when they be on opposite sides of each other? So we would expect silicon dioxide, which is really what makes up sand, like at your beach, and then ultimately if you do heat and pressure, you can make it into glass. It would look like this, okay? So that shape, we would call it, you guys see what it looks like? It looks like a line, it's called linear. That's a linear shape, okay? Bond angle, those of you guys who've taken geometry, you guys should have taken geometry. What's the bond angle on a line? The angle from this to this, it's 180 degrees. Okay, and then polarity. Okay, so now you guys on this, okay, so I'm going to remind you guys with polarity. If something's polar when the electrons are not evenly distributed, so if electrons are on one side more than the other, the side that they're on more frequently is going to be negative, and the side they're on less frequently is going to be positive. But if the electrons are evenly distributed, we'd say it's non-polar. So here's what you'd look. Okay, so we look at our molecule. And so I compare silicon and oxygen. So if I look on the periodic table, now we don't have electronegativity values, but look, oxygen is further to the top right. Remember, the more you are to the top right, the more electronegative you are. Oxygen's a lot closer to the top right than silicon is. That tells me that most likely I can predict oxygen is more electronegative than silicon. So when they're sharing these electrons, the electrons aren't evenly shared between it. The electrons are actually spending more of their time on the oxygen side. And so what I do is I point an arrow here. And then look at the electrons here that are being shared between oxygen and silicon. Once again, oxygen is more electronegative than silicon, so I would show an arrow going this way. But now overall, so it does have what we call polar bonds, but we want to know overall with the molecule, are the electrons evenly distributed in the molecule? Here's how you would tell. Basically, the easiest way is you look at your molecule and you see if it's symmetrical or not. Symmetrical means it's the same on both sides. If it's symmetrical, that's a good indication that the electrons are evenly distributed. They're not spending more time on one side of the molecule than the other. Then, therefore, it's non-polar. So you guys look at this molecule. Does it look symmetrical or is it not symmetrical? We say that's asymmetrical. Hopefully you guys realize it is symmetrical. What we would say is, what we could conclude is the electrons are evenly distributed, and therefore we would say it is non-polar. Non-polar. Okay, here I'll even write non-polar. Okay, last thing, Fisher projection. This one's easy. You guys, the Fisher projection is not going to look any different than what we have. You guys always want to show your lone pairs. So it looks the same as the Lewis structure. You guys are going to see where a Fisher projection could actually look different. Okay, now we've got BCl3. Once again, you guys remember the routine. We first count, we've got to do the Lewis structure. We count how many valence electrons. I look on my periodic table. I'll show you guys right here. Boron is right here, 3 over, so it has 3. Chlorine is way over here. If I count across, it's got 7 valence electrons. So each chlorine has 7, but I have 3 of them. 3 times 7 is 21, plus 3 from boron is 24. Okay? So then, once again, I'm going to put, now I have to arrange the elements. Okay? I'm going to put the element that I would expect to form the most bonds in the middle. Well, you guys look at chlorine here. Chlorine, like all the other halogens, only needs 1 valence electron in order to fill its outer shell. Therefore, we don't expect chlorine or any of the other halogens to only form 1 bond. We'd always put chlorine on the outside. And not to mention the fact that boron, you guys see it needs several more electrons. So anyways, I'm gonna put it boron in the middle, okay? I'm gonna put chlorines on the ends, outsides. Then what do I wanna do? You guys know that they're bound together, so I'm gonna put shared pairs. I've accounted for 2, 4, 6. 6 electrons so far, but the total was 24. 24 minus 6 is 18. So I still need to find a home for 18 electrons. So I'm gonna go 2, 4, 6, 8, 10, 12, 14, 16, 18. So I do that, and then you guys, right, so I've accounted for all the electrons. Now I check to see if the octet rule is satisfied. I look at chlorine, 2, 4, 6, 8. That's good. Look at this chlorine, 2, 4, 6, 8. Remember, we count this for both because they're being shared between the two nuclei. And then 2, 4, 6, 8. So everything looks good for chlorine, but then those of you guys who are already thinking ahead, you're like, wait, look at boron though. 2, 4, 6. You guys, I hate to bring up exceptions, but you know what? Boron is a frequent exception to the octet rule. I know I just got you guys getting used to it, but a lot of times boron will have less electrons and it'll still be in a very stable configuration. So nonetheless, guys, this is the correct Lewis structure, even though it deviates slightly from the octet rule. You just got to go with that. Okay, so now we're going to try to think of the shape. So now, imagine we've got, here, let's see here, guys. Let's see. Yeah, okay. So I got boron, and I got 3 chlorine atoms. So the question is, you guys remember, right? I have a center atom, and I've got 3 electron domains, 3 areas of electrons around the center atom. And remember, what do they want to do? They want to repel each other. They want to be as far apart from each other as possible. So the question is, what's the best way that 3 things can orient themselves around a central point so they can maximize their separation? Some people might be thinking, oh, a T-shape. Say a T-shape. Let me ask you guys think, is a T-shape the best they can do? I think some people are already thinking, hey, what's the best you can do? When you guys agree, not a T-shape, but a what shape? Wouldn't a Y shape or a peace sign? You do a peace sign or a Y shape. You guys look, isn't that a lot better separation than we would if we had a T shape? So it is this. And you guys will see what it looks like. It looks like a triangle, right? So to get the shape name, so it has a certain shape name. See, and if you guys were in the class, you'd be working with molecular models. Unfortunately, you're not, so that's just what we got. So that's where we get the name from, trigonal, kind of like a triangle, trigonal. And you guys will notice, you guys remember from geometry, you notice all the atoms, they're all in the same plane. So we call it trigonal planar. Okay, bond angle, some of you guys good? Remember, all around is 360, so if we divide it by 3, each angle is what? 120 degrees. In fact, 120 degrees is the best that 3 things could orient themselves to maximize separation. Now, polarity. You guys remember, we want to see, are the electrons evenly or unevenly distributed in this molecule? Remember, the best thing to do is look at the molecule and see if it looks symmetrical or not. Is it the same on both sides? It is symmetrical, so therefore we expect the electrons to be evenly distributed throughout the molecule. Therefore, we would say it is non-polar. You guys look at how finally we come to a Fisher projection, which is going to look slightly different than the Lewis structure. The Fisher projection, you want to make it look like it actually looks in 3-dimensional space. And you guys see here it looks kind of like a T if we did Lewis structure, but in actuality it's like a Y. So that's what I would show. I would draw a Y shape. Once again, don't forget the lone pairs. All right. So you guys, we're going to show 5 representative shapes. You guys, these won't be all the possible shapes. These are just the basic ones with their smaller molecules. There's some other ones, especially if you're in AP chemistry. You're going to go a little bit even more complex than this, but we want to get the basic fundamental shapes down. Okay, next one, CH4. Once again, guys, we've got the Lewis structure. What do? We do the number of valence electrons. I look, carbon, 4 over, it's got 4 valence electrons. Hydrogen only has 1, so I have 4 hydrogens, each with 1 is 4, plus the 4 from carbon is a total of 8. Obviously, which one are you guys going to put in the middle? You guys know, whenever you guys have carbon, always put carbon in the middle, because carbon forms up to 4 bonds, and not to mention the fact that hydrogens, you guys know hydrogens only form 1 bond, you always put hydrogens on the outside. So I would imagine you would do what I'm doing. I put a carbon in the middle, hydrogens, and what I'm going to do is I'm going to make bonds. I see that? And now Check it out, guys. 2, 4, 6, 8. That's all my electrons. I don't have to put lone pairs. Now I want to see if the octet's satisfied. Look at carbon. 2, 4, 6, 8. We're good. Now look at each hydrogen. Each hydrogen has 2 electrons orbiting its nucleus, and that's what you would expect. Because remember, hydrogen's the exception to the octet rule. It only needs a total of 2 electrons to fill its outer shell. Okay, so that is the Lewis structure. Question is, what does the shape look like? I know what some of you guys are thinking. Okay, so we got this. You're thinking, okay, 4 things. What's the best thing? 4 things. What are you guys thinking? What kind of shape? I know I can't hear you, but I'm hoping you guys are at least saying it to yourself right now. I'm just kind of, okay, that looks kind of like a whack. That's like a ghetto molecule right there. Okay, but you guys are probably thinking like a T shape, right? Now, if it's the T shape, what's the bond angle? If you could see it, what would be the bond angle? Isn't it 90 degrees? You guys know 90 degrees. You guys remember perpendicular from geometry. So, you guys, you know what? And this is where it could kind of be a little, I could see deceptive. You know what? If molecules were confined to just 2 dimensions, you know what? The best way they could separate is 90 degrees. But you guys, molecules matter. It's not confined to just 2 dimensions, height and width. There's height, width, and depth. So you know what? In 3 dimensions, here's what it's going to look like. And if you guys look closely, you guys should see it's not just 90-degree separation. Check it out. It's more than that. So that is actually what it looks like. And what we call this, you guys, here's where we get the name from. You guys will see it looks kind of like a pyramid. Well, a pyramid with how many sides though? 4 sides. And then that's where I'd ask, what do you think's the Latin for 4? Comes from, and there's a video game, most popular video game ever of all time. The most popular video game of all time is not Pac-Man. It ain't Fortnite, I'll tell you that. It is Tetris. That comes from the Latin, because you guys know Tetris is with the blocks, and the blocks have 4 sides. That's where you get tetra. Latin for 4 is tetra. That's where we get this name, tetrahedral. Now, you guys, if you're thinking about the bond angle, you guys should be able to at least predict something about the bond angle. You know the bond angle has to be more than what? Remember, we already talked about it. It has to be more than 90, but it has to be less than what? Doesn't it have to be less than 120 degrees? Because 120 degrees is the best thing. 3 things could orient themselves around the center point. Now we have 4 things, so you can imagine the bond angle is going to be less. And in actuality, you guys should be able to see it. Can you guys see it? Come on, guys. You guys can see that? Okay. That is, I would expect you guys to know this, 109.5 degrees Celsius. No, you wouldn't be expected to know that, but it is 109.5. It sounds like a radio station, right? But 109.5 degrees. You guys can see more than 90 degrees, but less than 120 degrees. Okay, once again, polar or non-polar molecule. Overall, you guys kind of going back to this. This one right here. If you look at the individual bonds, like between boron and chlorine, if you guys look on your periodic table, chlorine is way over farther to the right. Chlorine is much more electronegative than boron. So if I was showing the polarity of the bonds, I would show each bond is polar. But you guys remember, overall, we want to see is the molecule itself polar. And you remember what we did? This is going back to BCl3. We see it, does the molecule look symmetrical? So even though it's got polar bonds, but they're all spread out relatively evenly, so overall it's a non-polar molecule. The electrons are evenly distributed. So now I'm going to look on this one, CH4. So I look, is this symmetrical or not? And if you look, any way you look at it, you guys, it's the same on both sides. It is symmetrical, therefore we're thinking the electrons are evenly distributed. It doesn't have positive and negative sides. It's not like electrons are on one side of the molecule more than the other. It's symmetrical, we would say it is non-polar. Okay, you guys, this is where the Fisher projection gets kind of more sophisticated, because you'll notice, how is this different than the previous ones? It's got depth to it. So here's how we're going to show depth. So I'm going to show a carbon with a hydrogen on top. See that? Now check this out, guys. Look, you guys see hydrogens coming out at you in the camera there? We show that with this. Big old hydrogens coming out. You guys see the shade action? I took art. And then you guys see there's a hydrogen kind of going into the board. So we show that like this. Show a little bit of little hydrogen back there in the board. So you kind of show it like that. Okay, that's Fisher projection. All right, moving on, guys. We've got NH3. Once again, we've got to do the Lewis structure first if we're going to determine the shape. So nitrogen, if you count across on the periodic table, so hopefully you guys have a periodic table out while we're doing this, because I know you guys can't really see this. I'm just pointing to kind of remind you guys to regularly look at the periodic table. It's 5 across, so it has 5 valence. It has a total of 7 total electrons, but 5 are the valence electrons. That's what we're interested in, 5. And then 1 for each of the 3 hydrogens is a total of 8. Okay, so I've got 8 here. Obviously, what are you guys going to put in the middle? You guys should know. You're going to put nitrogen in the middle. And why is that? Because you always put hydrogens on the outside, guys. Always, always, always. So I'm going to put hydrogen, 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 hydrogen. What I'm going to do is I'm going to make bonds. 2, 4, 6. It's a total of 8, so I got to put a lone pair somewhere. Where would I put it? I'm going to put it on the nitrogen. I'm going to see, is everything all good? Look at nitrogen. 2, 4, 6, 8. Nitrogen's good, octet rule, and then you guys, each hydrogen has 2 valence electrons. You guys, that is the Lewis structure for, that's ammonia, guys. That's the main ingredient in your Windex, right? Okay, so now the question is, what would that look like? Remember how you do it. You look at the center atom, and you look at how many electron domains are around the center atom. How many areas of electrons? Look, it's got a shared pair, shared pair, shared pair, and a lone pair. It's got 4. So then that should remind us, what was the best way 4 things could orient themselves around a center point to maximize their separation? Wasn't it the tetrahedral shape? You guys remember this right here? Tetrahedral shape. But what's the only difference between this and this? Rather than a shared pair here, it's got a lone pair. So just imagine a lone pair of electrons here. It just doesn't have an atom attached. But you guys see, we end up with this shape. So you guys see how this shape ultimately originated from the tetrahedral shape. This is what we would predict according to Vsepr theory. Okay? So, shape name. If you guys think about it, doesn't it look like a triangle? Or I'm sorry, well, yeah, looks like a triangle. Okay, so that's where we get this triangular. But then again, at the same time, doesn't it look like a pyramid? So it's called triangular pyramidal. It's a triangular pyramidal shape. All right, last thing is, or not last thing, I'm sorry, we want to get the bond angle. Now you guys look, you think about it. The bond angle for tetrahedral was 109.5. That was the maximum angle that you could get for separation. The difference here is, rather than a shared pair of electrons, we just have a lone pair of electrons right here. You guys see that? So when you guys agree, wouldn't you expect the bond angle to be very similar to 109.5? But here's the difference. The question is, what do you guys think has more of a repulsive effect? A shared pair of electrons here, think about a shared pair and its repulsive effect on adjacent shared pairs, or not 2 electrons that are being shared, but 2 electrons that are lone pairs just orbiting the nitrogen. Do you think would they have a more repulsive or a less repulsive effect than a shared pair? Hopefully you guys are realizing if they're not being shared, they're going to be more concentrated around the nitrogen nucleus. Therefore, they're going to have more of a repulsive effect on these shared pair. And you guys, what's the result? It's going to push these bonds down. It's going to push these orbiting electrons down more. What's that going to do to the bond angles here? It's going to make them slightly less than the 109.5. In fact, the bond angle is actually 107 degrees. You guys see slightly less than that, but you guys see why? Because the lone pair is slightly more repulsive than a shared pair of electrons like in our tetrahedral one. Okay, next. Is this polar or non-polar? Are the electrons evenly or unevenly distributed? Well, we got to look. Is this a symmetrical molecule? Somebody would look at it and go, it looks symmetrical, but then all I have to do is do this. Is that symmetrical? Here we have shared pairs of electrons, here we have a lone pair of electrons. You guys, that's not symmetrical. That means the electrons are not evenly distributed. That means it's got positive and negative sides. Some electron density is greater on one side than the other. We would say it is polar. So note this, guys. This is our first polar molecule of all the ones so far. Okay, so now you guys, when I'm going to show the Fisher projection, you can imagine I got to show a 3-dimensional. So here I got my nitrogen, lone pair on the top, showing these hydrogens coming out. See the little shade action there? Guys, don't be jealous if you're not as good at drawers as I am. Okay, and then you guys, there's a hydrogen actually going into the board. Okay, see how that would look? Last thing I want to do is, we say if it's polar, we want to show where is the electron density greater. Well, you guys can imagine you have this lone pair, this naked pair of electrons on top, not being shared. That's going to make this, we would say the top of this molecule is partially negative and the bottom is partially positive. What are we saying by that? we're saying of all the electrons orbiting the center atom, they're going to spend more time on the top of the molecule, and thus makes the top of the molecule negative, than they are on the bottom, which makes that positive. Notice it's got slight polarity, an uneven distribution of electrons. Almost done here, guys. So, water. Valence electrons. You remember we're doing a little structure of valence electrons. If I count over on oxygen, if I count over, it's 6. Oxygen is 6. Hydrogen each have 1. That's a total of 8. Guys, obviously, which one are you going to put in the middle? You guys know hydrogen's always on the outside. So you put oxygen in the middle, hydrogen's on the outside. I'm going to make bonds. I've accounted for 2, 4. 4 electrons so far. There's a total of 8, so there's still 4 more. I have to show them as lone pairs. I would hope you would put them on the oxygen. If you guys put them on the hydrogen, you're going to see you're going to be off because you're going to count the electrons and it's not going to be right. So then I look and now I check to see if the octet's satisfied. 2, 4, 6, 8, we're good there. And each hydrogen has 2, which is what I would expect for hydrogen. So, the shape. Once again, you look at your center atom. Count how many electron domains are on the center atom. Hopefully you guys see, that also has 4. It's got a shared pair and a shared pair, that's 2. And it's got a lone pair and another lone pair. That's 1, 2, 3, 4. 4 areas. When you guys think of 4 things around a center point and maximizing their separation, what shape should come to mind? Once again, shouldn't it be tetrahedral? Same thing. Should be tetrahedral, right? But what's the difference? It only has 2 shared pairs, and the other 2, instead of 4 shared pairs, the other 2 are lone pairs. So I'm going to just take off a shared pair. So we have the same basic shape. You guys see that? Because I can see a lot of you guys, you would look at that, and if I ask you what's the shape, you guys are like, oh, that obviously looks linear. But now look at this, guys. Will it be linear? It's not going to be linear, and it's because you have these lone pairs of electrons on the center atom. And if you guys look at the shape, doesn't it look like a line that's what? That's bent. So we would say it is bent shaped. Bent. Some other people call it V-shaped, right? Because it looks like a V. Bent or V-shaped. Okay. Now, what I would like you guys to guess is, what do you guys think the bond angle is with this, if you had to guess? Think about our reasoning from before. You guys remember, right? If these were all shared pairs, you guys, what would be the bond angle? 109.5. And then you guys remember with ammonia, since one of them is a lone pair, more repulsive pushes down on these shared pairs, the bond angle got slightly less. What do you guys think if it's 2 lone pairs? Anyone want to throw it out? See if you could get it. Can't hear you. Are you guys shouting at home? You guys got to be a little louder. I can't hear you. What do you think it is? Okay, I think I heard it. It's 104.5 degrees Celsius. You guys notice, look, it's Celsius. Why am I saying Celsius? It's 104.5 degrees, slightly less than 107. Okay. You guys, water, this is really important, right? This is the stuff that we need to survive, so we want to know about water. So it's really important, guys, water. So now, are the electrons evenly or unevenly distributed? I see, does it look symmetrical? It looks kind of symmetrical, and then I just do this. Obviously, this side's not the same. We have these lone pairs. In fact, you guys, a lot of times, whenever you have a lone pair on the center atom, you're probably thinking it's polar, because the electrons aren't evenly distributed. This is indeed polar. Water is polar. You guys, if I'm going to show the Fisher projection, you guys can see I don't need to show any depth because they're all on one plane, but then I have the 2 lone pairs up here. So if it's polar, if you're going to say something's polar, you have to tell me what side is more electron dense and what side is less electron dense. And I would hope you guys would recognize, if you got lone pairs of electrons there, that's where there's going to be a greater electron density. That's partially negative on top, partially positive on the bottom. All right, guys, once again, these aren't all the possible shapes that exist, but there are 5 basic shapes. So you guys, I'm going to be giving you guys other compounds, not the same ones, and you guys are going to have to use the same kind of reasoning and ultimately determine what shape would you expect that compound to have, in actual 3-dimensional reality. All right, guys, until next time. Bye.